Half-life is basically the amount of time it takes for half of the atoms in our sample to decay, which means turning from a parent isotope into the daughter isotope. This is an intensive property. It doesn't matter how many you have, the half-life is going to be the same amount of time. It's different for every different isotope. Here's an example, carbon-14. Carbon-14 has a half-life of 5,730 years. It doesn't matter how much we have, it's going to take 5,730 years to have half that sample decay. Half-lives do vary depending on what substance we have. They vary from seconds to billions of years, and there's no way to determine which exact atom is going to decay, but we do know that we will get rid of half of the atoms in that amount of time. Okay, so we can't pinpoint exactly which atoms, but we can determine that within the average there's going to be half left. Here you should be able to look at this graph and understand what's happening in the graph here. If we look here, we've got 50%, so if you look here, percent remaining. If at 50% here, you should be able to take this graph, look at 50%, go across here till you hit the line, and understand that this would be one half-life, and this would be the amount that's left. Now sometimes when you see these graphs, instead of over here having the percentage, you might have the amount over here instead of on top of the graph too. So I could ask you a question at 2 half-lives, how much would be left of your sample, and you would go up to here and over, and this would be 25%, or it may also have 2.5 grams over here. So you should be able to do both depending on what's over here. Tell me the percentage or the amount depending what's included in your graph. Now some of the problems you're going to see, there's a couple here that I want to go through so you can kind of see the different examples that you might run into. Here it says that iodine-131 is used to destroy thyroid tissue in the treatment of an overactive thyroid. Half-life of iodine is 8 days. So if a hospital receives a shipment of 200 grams, how much would remain after 32 days? So we always start at 0 days, and then we increase by our half-life. So here we have 8 days. So we know one half-life is 8 days. So from 0 to 8 would be one half-life. Then from 8 to 16, so we just increase by 8 days each time. And then we add another 8, so that gives us 24 days. And then we would add our last 8 days, and that would be 32 days then. So this is where we want to get to. This would be one half-life, a second half-life, a third half-life, and a fourth half-life that it would take to get there. So at 0 days, we said we started with 200 grams. So at 8 days, we're going to have half of that left. At 16 days, we're going to have half of that left. At 24, we're going to have half of that left. And then at 32 days, we would have half of that left. So our answer here would be 12.5 grams is what we would have left after 32 days. So that's one type of half-life problem. Here, the half-life of uranium-232 is 7 years. How many half-lives would it take to get from 10 grams to 1.25 grams? So here, again, we're going to start at 0 days. Tells us here that our half-life this time is 70 years. So we would go 70, and then we would add another 70, so we would get 140. We would add another 70 and get 210. And I'm going to stop there. We may have to go further, but we'll figure it out here. So if we start with 10 grams, 70 days, we would have half of that. At 140, we would have half of that. And at 210 days, we would have half of that. And that's long enough to get us where we're going. So this, again, would be one half-life, 2 half-lives, 3 half-lives. Okay, so it would take us 3 half-lives to get our sample down to that amount. Okay. The next one down here, what is the percentage of radioactive nuclei left after 4 half-lives? So if we go from 1 to 2 to 3 to 4, 1 we would have 100%. At the end of 2 half-lives, we would have 50%. At the end of 3, we would have 25%. And at the end of 4 half-lives, 12%. except for I goofed up. Let's try this again. What did I forget here, you guys? I forgot 0. So we always have to start at 0. So we would have 100% at 0, then we would have 50%, we would have 25%, we would have 12.5%, and so at 4 half-lives we would have 6.25%. So always remember you must start at 0, and I forgot that. So you always have 100% at 0. And then our last one here, if we look at this problem, strontium is present in nuclear fallout. It can become dissolved in milk and then eventually be incorporated into our bones. So the places that have had nuclear meltdowns, nuclear power plants melting down, and the fallout is in the air, or an atomic bomb has been dropped, this is where the problem is that it's in the air and then it gets dissolved in the food sources, and then when people eat or drink that, it ends up getting in your bones, and that's why people get cancer and die from the radiation. Okay, so here what we want to look at is our equation that we want to use here is we have, oh, I need to get my pen working, sorry. The time that we're talking about is going to be multiplied times 1 over your half-life, so the time or length of the half-life. That's always going to tell us how many half-lives it takes to get there. Okay, so in this case, if we continue to read, we want to know how much will remain after 140.5 years. So that's our time that we're going to plug in. It tells us that our half-life is 28.1 years. So this should be a multiplication 1 over 28.1 years. And then that's going to tell us how many half-lives we have to go through. So when you take 1 divided by 28.1, take that multiplied by 140.5, and we end up with 5. So we know we're going to have 5 half-lives to get to our answer. Okay, so if we look, oops, if we look here, we're going to have to start, sorry you guys, we're going to have to start at 0, and we're going to go through 5 half-lives. So 0, 1, 2, 3, I don't have enough room, 4 and 5, and then again at 100% we're going to have the amount that they give us. So we have 104 kilograms at 0, and then half of that is 97 kilograms, and then 48.5 kilograms, and then 24.25 kilograms, and then 12.125. Okay, so what are we trying to get to? Let's go back to our question. It wants to know how much will remain after 140.5 years. Okay. So we've got at 0, we've got at 1, we've got at 2, we've got at 3, we've got at 4, and I didn't write very well, so we have to divide this by 1 more time, and we get 6.06 kilograms, and that would be our final answer. Okay. So these are 3 different ways that you may see half-life problems. Here you may have to use the equation time times 1 over the length or the time of a half-life is equal to the number of half-lives. Figure out your number of half-lives and then plug in and reduce here. You may have to figure out the percentages, always remembering you're at 100% at 0, and then you go half of that. Or you may be given a length of time and have to figure out how many half-lives that is and divide your number there.